Okay, thank you guys. In the previous class, we were talking about the number representation, that is the decimal number representation, and your signed number representation and unsigned number representation. And then for signed number, unsigned number representation, we have seen the signed magnitude, one's complement, and two's complement. In two's complement, to encoding a number or encoding with n bits for a positive number n, it is encoded with its binary representation only. For example, if you have the decimal number, suppose 2, the plus 2, it is simply represented as your plus 2's binary form. If it is in decimal, then 2's binary form is 1 0, and for plus we use the 0, so it gives as 1 0. But for negative numbers, it is encoded with the binary representation of its complement with the 2 to the power of n minus capital N. So note that for 2's complement, encoding the highest bit for a negative number is always 1. Always 1. So let us see some of the example. This is important for your assignment also. So as we said, there are 2-bit 2's complement encoding for a decimal values 1, 2, 3, -4, -3, -2, -1, and they choose equivalent complement binary encoding is. As we just saw, for 2's complement for any positive number, that is equal to its binary representation. So for 1, the binary representation is given 1 only, but we are using 3 bits, so we add 2 zeros, and it is positive, so obviously 001 is there. So similarly for 2, the binary representation for 2 is your 1 0, and for 3-bit encoding, it is added as your 0 1 0. So that is the binary representation. For 3, the binary representation is 1 1, and with 3 bits we use 0 1 1. Comes to the negative number of a binary whose 2's complement or the 2's complement binary encoding by adding the sign digit, we use the formula that 2 to the power of n minus capital N. So here we are using 3 bits, so 2 to the power of 3 is equal to 8, right? Where this minus n represents all these negative values. So here you can calculate that 8 minus the 2's complement binary encoding for -4 is, we can write 8 minus 4 is your 4. That's equivalent value is 1 0 0. The binary equivalent value is 1 0 0. Similarly for -3, you can see 2 to the power of 3 is 8, that is -3 is equal to your 5. Its binary equivalent value is 1 0 1. Whereas for your -2, 8 minus 2 is 6. Its binary equivalent value is 1 1 0. That you can find its binary equivalent value. Similarly for -1, 8 minus 1 is equal to 7. It's the 2's complement binary encoding is 1 1 1. Okay. Suppose if you have -5 number, you can write 8 minus 5 is equal to 3. That's equivalent binary number is 0 1 1. Right? And if 8 minus 6, suppose, then that's 2. That's binary equivalent value is 0 1 0. And if it is 7, suppose 8 minus 7 is equal to 1. That is equal to a 0 0 1. And if 8 minus 8, suppose, then that is 0. You will get the binary 2's complement binary representation is 0, 0, 0. Right? So this is the conversion of your positive number. The positive decimal number is simply its binary representation only. But for negative number, it takes its 2's complement encoding for the negative number, and that is evaluated with the 2 to the power of n minus capital N, where n is number of bits. Right? So now let us assume that instead of 3 bits, if 4-bit 2's complement is encoding, suppose 4-bit, that means what? Here you find 2 to the power of n minus capital N, where 4 bits means 2 to the power of 4 is equal to your 16, right? And suppose if I have the number that -5, -6, -7, -8, -9, -10, -11, then what is the 2's complement binary encoding, which are using 4 digits, which are using 4 bits, 4 bits. So then simply for the first one, you can simply write that 16 minus 5 is equal to 11. And for 11, the bit, the value is, you can write 1, 2, 4, your 8. Okay. So for 11, it is 8 plus 2 plus 1. So you can write it as 1, 0, 1, 1. So for 11, 16 minus 5, which is equal to 11, and its 2's complement, minus 5's 2's complement binary encoding is 1, 0, 1, 1. 1, 0, 1, 1. For minus 6, you can write 16 minus 6 is your 10. So for 10, you can write the 8 is 1. So 1, 0, 1, 0. So here you will find the 1, 0, 1, 0. Similarly, for minus 7, the 2's complement binary is 16 minus 7 is equal to your 9, which is equal to, here it is given 1011, here is 1010, and for this you will get the 1001. For 7 it is 1001. For minus 8's 2's complement binary is, you can write 16 minus 8 is equal to your the 8, that is equal to 1000. That is equal to 1000. You can see all ones are there, they represent the negative number. Okay, negative number. And you can find for minus 9, that is 16 minus 9 is equal to, you will find the 7, that is equal to your the 0, 1, 1, 1 equivalent value. Okay, so that is for 9, it is 0, 1, 1, 1. For minus 10, that is 16 minus 10 is equal to 6. You can represent this 6 as your 0, 1, 1, 0. 0, 1, 1, 0. And for minus 11, so 16 minus 11 is your 5. That is equal to, you can write this as your 0, 1, 0, 1. It is 0, 1, 0, 1. So this is the example of your 3-bit decimal into the 2's complement binary encoding, and 4-bit decimal into 2's complement binary encoding. So now let us see the floating point numbers. Let us see the floating point numbers. So what these floating point numbers? right? So the floating point representations of decimal numbers are essential to scientific computation using scientific notations. The standard for floating point representation is, we say, IEEE 754 standard. Okay, so in computer there is a trade-off between range and precision. So there are two precisions are there. We call the single precision and your double precision. Single precision and your double precision. Single precision means it takes 32 bits. 32 bits. Double precision takes 64 bits. 64 bits. Okay. So this single precision or double precision given a fixed number of binary digits, or we call bits. Precision can vary inversely with range, depends upon 32 bit or 64 bit. So in this, the lecture series, we overview the decimal to the floating point conversion. We try to do the decimal number to your floating point conversion in multi-instruction per second in MIPS floating point instructions, and how the registers are used for this floating point computation means they use this decimal to floating point conversions. So we have seen that an n-bit register can represent unsigned integer in the range. The unsigned integer, the unsigned the integers in the range from your 0 to 2 to the power of n minus 1, the ones complement that we have seen there, 2 to the power of n minus 1, as well as the signed integer, the signed integer that ranges from minus 2 to the power of n minus 2 to the power of n2, your minus 2 to the power of n minus 1 minus 1. So this is the range for your signed integers. So however, there are very large numbers, for example, 3.15576, which is 10 to the power of suppose 23, the large number, and very small number. It is very large number and the small number range. The very small number range is 10 to the power of minus 25. And there are some rational numbers with repeated digits. There are some rational number. However, there are very large numbers, very small numbers in floating point, the signed integers, and your very what you call the rational numbers with repeated digits. For example, 2 by 3, you will get the rational number with repeated digit, that's 6, 6, 6, 6, and it goes on, right? And irrationals such as your 2 to the power of suppose 1 by 2, the irrationals, and the transcendental numbers such as E is equal to your 2.718 dash dash dash. So all of which need to be presented in computers for scientific computations to be supported. So we call the manipulation of these type of numbers floating point arithmetic. We call all these type of numbers as floating point arithmetic. Floating point arithmetic. We call this the computations or the manipulations of this type of numbers as your floating point arithmetic, because the decimal point is not fixed in this example, right? So in C language, such variables are declared as your float data types. So these kind of variables declared as your the float data type. Float your data types. Okay, so now let us see the scientific notation and floating point representation. Scientific notation and your floating point representation. So see, the computers are also used to do the computational on the real numbers, as said, your floating point numbers. So the real numbers are written in the following form of your scientific notation: m multiplied with your 10 to the power of n. So that is the decimal form, which is having some fractions. So see some of the notations and the scientific notations and your decimal notations. Suppose if we have the decimal number 2, a decimal notation is this, then its scientific notation can be written as 2.0. It becomes your floating point, and 10 to the power of 0. So 10 to the power of 0 is equal to 1. So 2.0 multiplied with 1 is 2 only. That is round up with your integer 2. Suppose if we have the decimal notation 300, this can be written as 3 point. You put the dot here, and whatever two decimal points are there, they can simply multiplied with 2 to the power of 2. So it becomes 3 multiplied with 2 to the power of 2. That gives 300 only, right? So that can be written as your 3.0 multiplied with 2 to the power of 2. Suppose if I have 4,000, suppose, so it is 4,000 is there. So the 4 is at 1,000 position. It can be written as 4.0 into 10 to the power of 3. If I have 40,000, it can be written as 4.0 10 to the power of 4, and so on. If I have a decimal notation of some integer part and your fractional part, so then this can be written as you can take this point at the first digit point, and then how many this decimal point, how many positions it is moving, that is multiplied with 10 to the power of its number of positions. So here we can see, when this dot is positioned here, it is crossing 1, 2, 3, 4. So you can write 4 point something into 10 to the power of 4. This is very important. This point is, this dot is moved 4 position. Okay. So here, and then that is multiplied with how many positions it is moved? 1, 2, 3, 4. So multiplied with 4. So that gives your 4.24213232 multiplied with 10 to the power of 4. If you have the negative number, suppose if you have the negative numbers, okay, in decimal notation, that can be written as, okay, minus 2.0. It is 10 to the power of minus 1, because after dot it takes in negative direction. This side the positive direction. Okay, so when we are trying to shift this 2 into right side, then it is moving, this dot is moved one position to the left side, negative side. So it is given 10 to the power of minus 1. So these two parts are very important. As we said, the floating points are represented with the IEEE standard 747. IEEE standard of your the 754. The IEEE standard 754. So in this 754, how to represent any of this decimal number by following its scientific notations in the IEEE 754 format. Okay, so there are three steps involved in this. Before that, before discussing that, let us see how we call in the binary format. So the real numbers in binary format with the scientific notations can be represented similar to your decimal notations. So we can express the reals in binary format with a scientific notation. This topic is very important for your assignment and examination also. If you find any difficulties during this topic, please ask the question at the end of this lecture. Right. So we can write that the scientific format as in the binary format with scientific notation as one dot. You write the number here, and then it is multiplied with 2 to the power of your exponential part. 2 to the power of. Whereas in decimal we used some values. In our previous example we used 2, 3, 4 as your decimal part, and they are 2.0, 4.0, and they are multiplied with 10 to the power of your expression. But here we use in the binary format, means the base which is used is your 2. Okay. For example, if we have a number that 1.001010, okay, multiplied with 2 to the power of this. So from here you can see the terminologies which we used, for the representing this, the floating point representation. The terminology which we use is this part we called as your fraction. Okay, after dot, whatever part is there, we call it as your fraction of the real number, while this trees we call these exponents, and here we use 2, so it is base 2. If we use 10, it is base 10. If we use 8, it is base 8. If we use 16, if you use 16, it is base 16 or hexabase. So here the dot which we are using, the dot before the fraction part is called your binary point. If it is the base 10, suppose, then we call decimal point. If it is 8, suppose, then we call it as octal point, which is the similar to your decimal point part. And note that there is only one digit before the binary point, and that digit is always 1 in binary. Okay, so always only one point, always before this dot, always 1 should be there. We called it as your the only one digit before this binary point, and that digit is always 1. If it is decimal, suppose, okay, if it is decimal, suppose only one decimal digit, as we know that the decimal digits are the base 10. We know the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and your 9. So before dot, only one digit should be there. Only one digit should be there, and that digit should not be 0. It may be 1, it may be 2, it may be 3. So only one digit will be there, and the remaining part is converted into a fraction. When it is converted into fraction, it is multiplied with its positions. How many positions that number, this dot is moved. Okay, so since the digits can only be 1 or 0 in binary, we can always remove leading zeros and leaving a 1 before the decimal point. Right? So in computer arithmetic, that supports the binary real numbers in their scientific format, that we called as your floating point, I just said. And as the position of the binary point is moving, that depending on the value of your exponent, if value of exponent is negative, then it is moving in a right direction. If it is positive, it is moving in a left direction. So an integer is fixed point. The integer is fixed point, as the binary point is always at the end of the integer. At the end of the integer. So in C language, we are call it as your floating values. So to encoding the float values with these bits by following this IEEE 754 format. So this derived from the scientific notation, encoding this float with bits derived from the scientific notation. Which notation? The IEEE 754 notation. A binary floating point number is uniquely identified by its sign, because we are talking about the signed, the floating points, signed floating points, and its fraction and exponent. These are three major components. So therefore, computers encode floats with only sign, fraction, and exponent. So whatever the fraction part that we use in a number, suppose 1.10001111 and something 2 to the power of suppose 15, like, so whatever this fraction part is there, this fraction part we also call it as your mantissa. We call it as your mantissa. Okay. So now, as we said, there are two precisions are there. One is your single precision, and another one is your double precision. So single precision use the 32 bits length of your floating point. Double use the 64 bits, the precisions. So let us see one by one. In a 32-bit float, you can see here the first bit, or we call the bit position from 30 to 31 is 1 bit, that is reserved for representing the sign, and 8 bits used for your exponent purpose, and 23 bits used for your fractional part. This sign bit for 1, and for fractional 23 bits are used. For exponential it use the 8 bits. Okay, so total 1 plus 8 plus 23 is equal to your 32 bits. So it is a single precision IEEE 754 format of representing your floating point, of representation of your floating point. So let us see an example. Let us consider an example. So how it can be represented using the single precision. Okay. So in single precision, as we are saying that it uses in single precision, it uses the 32 bit. Okay, and it follows the IEEE format, as it says that one is your the sign bit, that is your sign bit, and you will have the fractional part, one dot your fractional part, and you are having the exponential part. So here this exponential part uses this bias. We call uses this bias. So what is this bias? This bias is this exponential part bias is always for 32 bit, it is gives the represented as E minus 127, or this is the expression which is used for single bias, or in simply it can be written as your, for single precision, it will be written as your, 1 dot n, 1 dot n, which is multiplied with your 2 to the power of e minus 127. This is very important, this equation. For your double precision, it is 1 dot, for binary 1, it is 1 dot n, 1 dot n, which is multiplied with 2 to the power of e minus 1023. That is the IEEE standard format. Okay, so now let us see the example. Let us see the example. Let me just change the color. Okay, right. So, for example, if I have the binary number, if I have the binary number, suppose 1259 dot your 125 base 10. If I want to represent this, if I want to represent this in, the encoding this floating point in the binary representation, what I need to do, there are certain rules. Okay, what is that rule? The rule says that there will be step 1. In step 1, convert this decimal to your binary. Then in step 2, you should normalize it. Okay, so in normalize, it means take the binary into leftmost side, and only one digit should be there on left side of your dot. Okay, and then in step 3, we write this into your IEEE 754 format of a floating point encoding. Okay, so now let us see first what we need to do. The first step, it says that we need to okay, so first we need to convert this decimal into your binary format. So what we do, as we saw in previous examples, the integer part will be converted into binary, that is decimal to binary, by doing division operation, and fractional part by doing the multiplication operation. Okay, so now let us see the example of converting this one. In this, you can see how we converted 1259 convert into binary. So use the radix 2. So that is converted into 1. It is divided with 629. So what the remainder is 1. Then this is divided with 2. So that is 312. Okay, it gives the result. The remainder is 1. When you convert this, then it is divided with 156. So it gives the remainder 0. When you convert this, 2 divided with your 78, then it gives the result 0. Then divide this with 2, that is 39. The result is your 0. Okay, remainder is 0. Then divide this with 19, you will find the remainder is 1. And divide this with 2, then 2 9s are 18, remainder is 1. Then 2 4s are 8, remainder is 1. And 2 2s are 4, remainder is 0. And 2 1s are 2, remainder is 0. So you will get this, the binary equivalent value. The binary equivalent value for this, what do you call this decimal part, that you will get the value is 1 0, because you need to take from in a reverse order, right? 1 0 0 1 0 0, then 1 1 1, 1 0 0 1 1 1, 0 0 0 1 1. So now we need to find the fractional part. Okay, for fractional, what we do for this fractional part, 0.125 multiplied with 2, it will give the result 0.250, right? So then from here you need to find the integer portion. The integer portion of this one is 0, right? Then the fractional portion of this 0.254 is again multiplied with 2. That gives the result where 0 uh, 0.50. From here you will get the integer part is 0. Then 0.50 multiplied with 2, so you will get the value 1.0. Integer part is your 1. Integer part is 1. So it is written in a same computational order. So that is your 0 0 1, 0 0 1. So you can write 0 0 1. So that is the binary equivalent to this decimal. So first step is over. The second one is, in the second step is, what we need to do, we need to normalize this number. Normalize this number means your dot should be, normalize this number means your dot should be shifted. Okay. In normalization, your dot should be shifted to a position where it should have only one digit on left side of the dot and the remaining on the right side and fractional side. So that is your step 2. That is normalization. Normalization. So this can be written as, this is equal to, when dot is shifted here, it gives one dot. Okay. How many positions the dot is shifted to left side? 1 2 3 4 5 6 7 8 9 10 positions, right? 10 positions. So just remember that, and you can write this all numbers like 0 0 1 1 1, 0 0 0 1 1, and the last three parts are your 0 0 1, which is multiplied with 2 to the power of 10 positions. It is shifted. So that we call your normalization. That we call the normalization. And then encoding it into the third step is IEEE 754. IEEE 754. In IEEE 754, what it says, one bit is, the leftmost bit is your sign bit. Then the next 8 bits for your exponent, and the next one is your the fractional bit. So now we need to find out this exponent value. We need to find this exponent value. In the exponent value, you can see here. Okay, let me check whether it. Okay, so as per this equation, it says that your 2 to the power of e minus 127 is equal to, here 2 to the power of 10 is there, right? That means your e is equal to, e minus 127 is equal to your 10. So your e is equal to your 137. So convert this 137 decimal into binary. So as simply, what we did here, so it gives the result. This 127 binary value is, if you compute, you find 1 0 0 0 1 0 0 1. So this is the binary equivalent. Okay. So then now you can fix. Now you can fill this IEEE 754 format. First bit is, our number is positive number. So your sign bit is 1. Okay, sign bit is 1. Then the exponent is 8 bits. Now see the exponent value. This exponent value is 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. So you can fill that the exponent value. Okay, you can write this exponent value 8 bits as your 1, 0, 0, 0, or 1, 0, 0, 1. Okay, and then 23 bits of your fractional. So our fractional part is this one. What is that? 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 0, 0, 1. This is the fractional part. Okay, so sign bit is 1 bit, 1 bit. Your fractional part is 8 bits, 8 bits, and this one is 23 bits, 23 bits, right? So how many bits are there here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 30. So remaining 10 bits you can fill with leading zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total it is a 32-bit encoding. 32-bit encoding, 1 bit for sign, 8 bit for your reason, and 23 bit for your fractional. So this total is your what you call encoding of your floating number with 32 bit in single precision. Okay, so next, let us try to what you call do one more example so that you can better understand. Okay, let me do the another example. So in this example, suppose example 2, consider the binary float value. The binary float value is your what you call 500.3 with base 10. So what we need to do first, we need to convert this binary float value into your binary format, your binary format. So for 500, if you do this operation like the previous which we have done, so divide that 500 divided with 2, so that is 250 gives the remainder as your 0. Then divide this with 2, so that is 125, remainder is 0. Then divide this with your 2, so that is 62, remainder is 1. Divide this with 2, 2 3s are and 2 1s are, is remainder is 0. Then divide this with 2, 15, remainder is your 1, and 2 sevens are, the remainder is 1. Then divide this, 2 threes are, remainder is 1, and 2 ones are, remainder is 1. So when you write this in a reverse order, so then you will get this value as the binary equivalent of your 500 is there is 1, 2, 3, 4, 5 ones, 1, 2, 3, 4, 5, and 0, 1, 0, 0. Now we need to find the fractional part. Okay, so for fractional part, for this 3, what we need to do? We need to do the multiplication of this. So 0.3 multiplied with 2. So you will get and this procedure continued. You will get this 0.6, and this is continued. So you will get a value of this. So this 0.6 again multiplied with 2. So that is 1.2. Then 0.2 multiplied with 2. So that gives your 0.4. Then 0.4 multiplied with 2. That gives 0.8. then this 0.8 multiplied with 2, that gives 1.6. Now 0.6, the fractional part, multiplied with 2, it gives your 1.2. Okay, so from here you can see 0.6, 1.2, again, it continues. It continues, right? So from here you can derive this, that the reasons are 0, 1, 0, 0, 1, because it repeats again, 0.6, 0.2, then your 0.4 comes, then 0.8 comes. So it follows 0, 1, 0, 0. From here it is going to repeat. So you'll find 0, 1, 0, 0, 1, then 1001, 1001, this continues. So this is the binary format of your fraction. So you can write here as 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, and this continues. That is the binary equivalent. So we converted the decimal into your binary, converted decimal into a binary. So second, what we need to do, we need to do the normalization. We need to do the normalization. So in normalization, what we need to do, we move this decimal to the leftmost by keeping only one digit on left side of your decimal. So how many bits it is moving? 1, 2, 3, 4, 5, 6, 7, 8. 8, right? So it can be written as, in step 2, it can be written as 1 dot the remaining bits. 1, 1, 1, 1, 0, 1, 0, 0. Then this repeats 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, and so, which is multiplied with 2 to the power of 8 bits. You moved 8 bits. You moved 8 bits. And then we need to fill this. Into this procedure. We called it as your normalization. Normalization, right? So first we did this conversion. The conversion from decimal to your binary. Then second one is normalization. Third step, you need to fill into your the IEEE. Fill into your IEEE float encoding with the bits. So here, as you know, this is a positive number. So your first bit, sign bit, then your 8-bit exponential, and 23 bits of your fraction part. So our sign bit here is, let me just use the different pen. Okay, the sign bit here is positive, so sign bit is 0, right? And then the exponential part is 8. As we know that this exponential is given as your 2 to the power of e minus 127 is equal to 2 to the power of 8. So e minus 127 is equal to, because same base are there, that is 8. So you will find e is equal to 127 plus 8, that is equal to your 135, that is in decimal. So it's binary equivalent of your 135. If you convert this, you may get 1000011 into your binary form. So then you can fill this exponent with how many digits? 8 digits. So that is your 1000011. 1, 2, 3, 4, 5, 6, 7. I don't know if I'm right or wrong. For 135, It is, if it is converted, then you will find that, just a second, 135. You get two twos. Just a second, please. Okay, so it fills with this number, the one, suppose, I think this is equivalent to 135, and then the fractional part, that comes from this number. So that is what is the fractional part here? 1 1 1 1 0 1 0 0 0 1 0 0 1 1 0 0 1 1 0 0 1, and this continues. So then you need to check the total bits. Sign bit, your exponential, and your fractional part. So here is 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 23. So this is required, right? So this total is 32 bit for encoding of your the number, floating point number 5003, 5003, 500.3. Okay. So now let us examine another case. Let us examine the another case of your example 3. Suppose if we have a the decimal number in a negative one, okay. So what is, let us consider, I have a number minus 1.75, which is 10 to the power of 50. That is the decimal number. Okay, so then what we need to do, first we need to convert this into the binary one. So to convert this into a binary one, first we need to convert this decimal into binary. So to convert this decimal into binary, that means what our question is, 2 to the power of how much is equal to your 10 to the power of 50. So to do that, we use the logarithmic algorithm, so that we can write this as your log 2 to the power of x is equal to, apply log on both the side, that log your 10 to the power of 15. It can be written as x log 2 is equal to your 15 log 10. Then to get this log 2, you can divide this on both the side by your log 2, this your log 2. So then log 2 goes cancel. You will get x is equal to 15 multiplied by your log 10 divided by your log 2. So as we know, the log 10 value is equal to 1 and your log 2 value is almost 0.3. So then it can be written as your so x is equal to from here you can find x is equal to 15 into log 10 means 1 divided by 0.3. So this can be written as your x is equal to 15 into 1 into 10 divided by your 3. So 3 ones are 3 15, 3 5s are. So you will get x is equal to 50. X is equal to your 50. So from here you can get this x value. X is equal to 50. That means your 10 to the power of 15 is equal to 2 to the power of 50. Now try to convert this portion now. Okay, in integer part, in integer 1 of your decimal 10 is equal to your 1 of your binary. Then 0.75, 0.75 of your fraction 10, which is equal to, if you convert this into binary, it is equal to your binary equivalent, your 1 1. If you do the same operation which we did, then this total number is equal to your binary format as your 1.11 in the binary. Sorry, up to here. Okay. So then you can write this that the minus 1.75 into 10 to the power of 15 is equal to your minus of your binary format, that is 1.11 into 2 to the power of 50, which we got here equivalent, right? And then from here, if you start filling this, this format, the sign bit here is it is minus value, so sign bit is 1. Your sign bit is 1. Then your exponent bits are your 50. So this 50 can be calculated. How we are going to calculate, convert this 50? Okay. So this 50, we can say that E is equal to 127 plus your 50. Right? So that gives your 177. And its equivalent binary value is 1011 and 0001. That is binary equivalent. So your exponent value here is 10110001. And then this is your 8-bit exponent part, and then comes your 23-bit of your fractional part. So that 23-bit is your fractional part here, 110. So that is 11. So you have only 11. Remaining bits you can fill with the 0. Okay. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So this is a representation of your negative numbered IEEE IEEE 754 format or encoding of your floating number. So this, we call this as your the example. These are the examples for your encoding the floating points. Okay. So now comes to the precision period of your 1 bit for the sign, 1 bit for sign, as just we seen, and 8 bits for your exponent and 23 bits for your fraction. So the maximum positive float with this 32-bit encoding is the maximum number is, the large number is 1 plus 2 to the power of 23 multiplied with 2 to the power of 127. So that is roughly 10 to the power of 38. And the minimum positive float for your 32-bit encoding is your 2 minus 2 to the power of minus 32 multiplied with your 2 to the power of minus 26, that is roughly 10 to the power of minus 38 bits. All other bits becomes your overflow and underflow. All other numbers out of these ranges comes as your overflow and underflow. If you go with the same procedure for your double precision, 1 bit for sign and 11 bits for the exponent, and your 52 bits, not 32, 52 bits for your fraction. So this is the format of your double precision of your IEEE 754 format. Okay. So then, there are some bits which are reserved. There are some bits which are reserved are the special values of the exponent and the fraction. Exponent and the fraction, that is 1 point to your n to your 2 to the power of your the exponent and your fraction value, these values, okay, which are reserved to represent the special cases. Suppose if the exponent is 0, if this exponent is 0 and your fraction is also 0, then the value is 0. If the exponent is all ones, all these 8 bits are ones, suppose the binary form of this one, okay, if all ones, that means, and if you don't have any fraction, then it leads to your infinity. If the exponent is 0 and your fraction is not 0, then there is a denormalized position. The fraction may be somewhere like 4, 5, 6, 7, fraction is and 2, 3, 4 somewhere. So no leading one before this binary in terms of binary. If it is 1, 1, 0, 0, 0 dot 0, 1, 1, 1, 1 means it is not, it is denormalized. No leading one before the binary point. And if the exponent is all ones and fraction is not 0, then not a number. It is not a number which falls in the range of 10 to the power of 38 to your 10 to the power of minus 38, the range which we discussed. That number doesn't falls in this range, right? So this floating point computations, there are the standard algorithms for this, converting the between binary floats to your decimal point and doing the summation, abstraction, subtraction, multiplication, and division. But it will not cover these algorithms. I mean, I'm not going to cover these algorithms, but you can easily, find these algorithms online or in my textbook for your more knowledge or the more information. So with this, I would like to stop this session here. With this, I would like to stop the session.